Hello everyone, welcome to this video. In this video, we'll be continuing with more examples from homomorphism, where we are discussing about the kernel of the homomorphism. So here we have some mapping phi, which is mapping the set of integers to the set of integers modulo n. And this mapping is defined like this. If you input some integer here, you would have the answer as its mod n calculated, right? So this mapping is a homomorphism. We have already seen this thing. Now what would be the kernel here? So for that, for the kernel, you need to identify what is the identity element present here. The identity element is 0 actually, right? And when all will you get 0, you will get 0 when you have 0, and then you have n, then you have 2n, then you have 3n, 4n, 5n, and so on. Why? Because when you calculate n mod n, you will get 0. When you calculate 2n mod n, you would again get 0, right? When you calculate 3n mod n, you will again get 0, and so on for each of the terms. So you see, you obtain 0 when you have 0, n, 2n, 3n, 4n, 5n, and so on. Therefore, your kernel is the set which is generated by n. Correct? Why this is so? As I've told you, if you take any multiple of n here and then calculate its mod n, you will get 0, which is the identity element of Zn. Hence, this forms the kernel of the given mapping phi. Right? Similarly, for the next map, we are now defining the mapping phi from the set of all non-zero real numbers to the set of non-zero real numbers, such that phi of x is equals to x square. Right? Now, in order to determine the kernel here for this homomorphism, we need to identify under multiplication what is the identity here. It is 1. So we are looking for all those phi of x such that it is equal to 1. So what is the value of x from here? X could either be plus 1, it could be minus 1. Hence our kernel becomes equal to plus 1 or minus 1. Right? Moving forward on to our sixth example, we already studied about linear algebra. In linear algebra, we know every linear transformation, that is basically a homomorphism, right? And when we take an invertible linear transformation, that means linear transformation which is both 1, 1 and on 2, it is also an isomorphism, which has also been discussed in the last two videos, right? So here, what is the kernel of this mapping? The kernel of this mapping, which is a homomorphism, is basically the null space of linear transformation. Correct? Hence, we have the kernel phi as the null space of a linear transformation. Correct? Okay. Then moving forward on to our last example, we know any isomorphism is a homomorphism. Why? Because isomorphism is a mapping which is 1, 1, which is on 2, and which is operation preserving, right? Whereas this homomorphism is a mapping which is only operation preserving. Hence, we clearly see an isomorphism is definitely a homomorphism. So what would be the kernel of such a mapping? So you see, the kernel of this isomorphism, that is a trivial subgroup identity. Why this is so? Can you think at once why we have a trivial subgroup as the kernel here? Because for a bijective mapping, each element of domain is associated to only one element in the range. Because suppose, let's see, this is our group G, this is our group G bar, correct? And we have mapping phi, which is defined as an isomorphism. Hence, it is a bijective map, right? So it would associate each member in G to a single element in G bar. So that means, you know, obviously in every mapping, the identity is associated to identity. So obviously from here also, identity would be associated with identity, and no other element from here would be associated with identity. Why? Because we have in a bijective mapping, each element of domain is associated to only one element in the range, right? That is why we have only in the kernel the identity element with us. Otherwise, for any other mapping which is not a bijective mapping, right? If we have some group G, if we have some group G bar, and we define the map to be psi, then there might be elements which are mapping to the single element identity here. So then the list of those elements would form the kernel of that mapping, right? And that is what we are looking and that is what is the definition for kernel, and that is what we are looking for in each example when we are discussing about the kernel of some mapping. So you see, this is the difference. That is why we have a trivial subgroup here in this particular case for an isomorphism which is a homomorphism. So I hope you understood these examples well and this concept of kernel of some homomorphism well. Well, that is it for this video. Thank you for watching.